let's try to get an idea of the fact which is quite known that on the Bloch sphere what lies are your pure states, and inside the Bloch sphere what lies, the states lie, are the mixed states. Let's see why. So if it is a Bloch sphere, then this Bloch vector which represents a quantum state here is going to represent a pure state. And if I have a state here and there is another Bloch vector, then this represents a mixed state. Let's say V1 and V2. Certainly then we could see that V2 is lesser than V1, right? The magnitude of it. So what we can conclude the fact that if the modulus of V is 1, because you know in the Bloch sphere the radius is 1, because all the Bloch vectors has to be of unit length, okay, to give a unit probability. So if the magnitude is 1, then it's a pure state, and if the magnitude of the Bloch vector is less than 1, so the point is inside here somewhere, then it's a mixed state. Okay. Not only so, this could be directly in fact generalized from the idea that the trace of rho square equals to 1 implies a pure state, and less than 1 implies a mixed state. Let's try to connect these two ideas. How they are derivable from each other. Okay, let's remember that our rho is nothing but half identity times, so it's nothing but a 2 cross 2 identity, this Bloch vector times this sigma matrix. Okay, now we have to square it and take the rho square, right, and then again take the trace of it. So to square it, what we can do is we could multiply this thing twice. Okay, another 1 by 2, so this becomes 1 by 4, and then identity plus V square. But then I don't know how a dot product would be squared. It seems like difficult, but then of course it is doable. What I do is, I take the rho matrix as the following one, in terms of V1, V2 and V3. So I take it as 1 plus V3, 1 minus V3, V1 minus V2, V1 minus IV2, and V1 plus IV2. Yeah, so this we saw in our last lecture, this particular form, which was just couple of steps before this step. So I just take it as this and then try to calculate the rho square, because this would become easy, as we would see. Rho square would then become 1 plus V3, V1 plus IV2, V1 plus IV2, V1 minus IV2, 1 minus V3, again multiplied 1 plus V3, V1 minus IV2, 1 plus IV2. Okay, let's multiply now. 1 plus v3, 1 plus v3. So here I get a 1 plus v3 square. And then v1 minus iv2, v1 plus iv2. So they are complex conjugate of each other. So here I get it's v1 square plus v2 square. Okay. Then we multiply this thing with this row. Okay. So okay, let's first obtain this term. Okay, this term. So to obtain this term, I should multiply this with this. So when I multiply this with this, v1 iv2, v1 plus iv2, this becomes v1 square plus v2 square, and then I multiply this term with this term, it becomes 1 minus v3 square, 1 minus v3. And I am simply not caring about this term, basically for the following reason, that I need the trace of rho square at the end. So for trace I just need this diagonal term. So let me not, I'm a bit lazy, let me not calculate them. Okay. Then the trace of rho square becomes 1 plus v3 square, 1 plus v3 square plus v1 square plus v2 square plus v1 square plus v2 square plus 1 minus v3 square. This then equals to 1 plus v3 square plus 2v3 plus all these terms, then 1 plus v3 square minus 2v3. And you could see this 2v3 and this 2v3 cancels each other, and what I am left with is 2 plus 2 times v1 square plus 2 times v2 square plus 2 times v3 square. Right? Okay. So that is the general value for the trace of rho square. If this is rho, if this is rho, half of identity plus v sigma, then trace of rho square is 2 times identity plus v vector. Sorry, it's not identity. 1 plus because you can see that v1 square plus v2 square plus v3 square is nothing but v mod square. I take a 2 common out of it. Okay, alright. We did one simple mistake in the calculation. If you remember, from this row, when I square it, this half gives me a 1 by 4. So that 1 by 4 when multiplied with this 2, it gives me a 1 by 2 here actually. Alright, I'm sorry. This implies then, if it is pure state, okay, for pure we know that rho square, trace of rho square equals to 1. So I get half times 1 plus v mod square to be 1, which implies 1 plus v mod square to be 2, and thus v mod square thus v mod square equals to 1. and if it is mixed state, then the trace of rho square is less than 1. So this particular 1 plus p naught square becomes less than 1. So I get it to be 1 plus v mod square less than 2. So I subtract 1 from both the sides to get v mod square less than 1. Okay. And then I generalize it to the magnitude should be equal to 1 and the magnitude should be 1. Okay. And yeah, this is how we could connect the trace definition of distinguishing a pure and mixed state to the Bloch vector definition of distinguishing the pure and mixed state. Thank you.